0.9, then from this mid to the end is 4.1, then it is 0.9 between the two bogies, two cars, sorry, and then it follows in the same manner. And this wheel spacing is 2.7 meters, which is given in this loading. So what you have to do, you have to find these ordinates that start from 0. That first vehicle enter at the first vehicle, it is at 0 location, and the location of the rest of the vehicles is the distance between them. So we have just the second vehicle as 2.7 from the first, and then third you have to enter from the second. So third wheel is at the distance of 12.2 from the second wheel. So in the similar fashion, you have to just calculate these values for just one car, and then these are the similar for the rest of the 15 cars. Then after this it is 2.7, then again 12.2, then 2.7, then 6.4, then it follows the similar pattern. So what you have to do is you have to just prepare an Excel for this by in the same format as given here, that at the first it is written the Excel number, that first, second, third, fourth, and at the second it is distance from first to second, second to third, third to fourth, and in similar fashion up to the last Excel. And in the last column you have to just enter the Excel load. So what I can do, I can explain the program how we'll do that. So what you have to do, you have to just go to this load dynamic nodes, this train load generator, and then here just select this user defined, and just either you can what you can do, you can enter here at 0 location the force is 166.67 kilonewton, and just add after that at 2.7 it is again the force remains same, and again after 12.2 the force remains same. In this similar way you can enter for all the excels, or what you can do is you can just or either way what you can do is you can just import your Excel file prepared in the similar way. So I'll show you my prepared Excel first. Is not here. That is so. This is my prepared Excel. Just not need this column. Just three columns are required. So at the first Excel is at the 0 location with Excel load this. The similar way it is prepared for all the 64 Excel, that is 16 coaches, 4 Excel in the each coach. So what you have to do is you have to just go to the program and import this file. So it is you have to select the directory. I have saved in the current directory only, and just open this. If you have opened this, so you can see on the screen now this loading is defined from the Excel. All 64 Excels are defined here. You can enter the number of that is the lane from here. So what I can do is just demonstrate how to define that. For that, what I'll do, I'll just open the loading slab, which is used for the definition of track. So that is, I'll just activate this only. So our track is the middle one, which is demonstrated yesterday. You just select these points here, then load case name 1, vehicle. For this load case, I'm selecting the name 1, and this is applied for the dynamic load case 1. then train velocity, let I'll consider 1. So this 1 kilometer per hour speed is considered as the static speed. So this is used further for calculation of dynamic amplification factor due to these dynamic moving loads. So that is why this 1 kilometer per hour speed is defined here. So if here, from here you can show the graph how these axles are at particular node. This is at the starting node, then at next node, at next node. It will generate these type of time histories at each of this node. You can also see the distance from of these nodes from here. And for the further amplification, for the further application of these uh, train load for different load cases, what you can do is you can just save this arrangement as a WZD file in your program in your system. That I'll save it as Vande Bharat trial 1. So in the next time, what you have to do is, if I just press OK, I think in the next time, what you have to do is you have to just open that saved file and open that file. So already everything is defined here. You have to just change the load case name for which you are going to do and thus velocity at the train speed and just press OK. In the similar way you can do for all the speeds. So how to decide that from which speed range we have to start and what is the speed interval that we have to take here. So this is already explained that it already generate the time forcing functions and dynamic nodal loads. Then how to decide that from which speed we have to start and where we have to end, and then what is the speed interval. So for that, these guidelines are given that we have to start from 144 kilometer per hour up to 1.2 times the target speed. So here the target speed I am using is 200 kilometer per hour. So what we have to do is we have to done the analysis for 1.2 times 200, that is up to 240 starting from 144. But we have to consider the resonating speeds at least up to third harmonics of the resonating speed. So this is already discussed by sir in the morning, how to calculate this resonating speed. So for this my bridge first frequency is 30.47 radian per second. Then the car length for this loading is 24. So based on this, these three harmonics, first three harmonics of this harmonics depend on this I value. So these first three harmonics of primary resonating speeds are calculated here. Then these two speeds are in close. This 140 is close to 144, and this 209 is in between our range of interest. So what we'll do? I had defined smaller interval along this 139 and this 210. And in general, 10 kilometer per hour speed interval is taken. So total will start from 139, 140, 138, that's smaller at this range, then 150, 160, 170, up to 200, and then 208, 9, 10, and then 20, 30, 40. Like that we have to enter. So how to enter, that already explained in the program. Just you have to enter, and you can also see from here that how these loads are applied at each node. So at each node, different these time history functions are applied by the program. So you can see here a number of time forcing functions are defined. You can see the property of any of the function from here. And in similar fashion, for all of these forcing functions, a number of load cases, that is dynamic nodal loads, are applied by the program itself. from just one single command, that is a train load generator. It will do all of these things by itself. So in this way, we can define the dynamic loads, dynamic moving loads to the program, and then we have to just press to analyze these results. So I have already analyzed these results. So now now what we have to do, we have to just see how to get the results from the software and how to interpret them. So the results which are demonstrated here are the variation of acceleration with time, the Fourier spectra of the results to identify that what is the predominant frequency in the result output file, then vertical displacements, and then vertical acceleration. So for displacement and acceleration, these are the limits provided by the UIC, which are already discussed in the morning. So for 32 meter span, we have just take the maximum value, that our speed is up to 240, so we can take it L by D, that is 1.5, that is in meters. If mm you can do, that is 1500. And for deck acceleration, our track is ballasty track, so that is 3.43 meter per second square. So to check the results, what you have to do is you have to just go to this result tab. Then first I am showing how you can see the variation of acceleration or displacement with time. How to see that graphs in the program. So for that, what you have to do is you have to just go to this time history graphs. In this similar fashion, you can generate the graphs for time history analysis also, so that are not shown intentionally there, that I'm showing here. So what you have to do is you have to go to this TH graph, then this window pop up. Here you have to go to this define or modify function. Here you have to define that at which node and for which load case you want to see the results. From here you have to select the displacement, velocity, acceleration, or if you want the variation of forces, then you can select here the forces also. Just I can show here only. It is not responding right now. So we will just wait, or we can close and reopen. I'll reopen this so that you see. It will take some time to open. So what we have to do is, for seeing the results, we have to define here a function. So we want to see the mid span acceleration for the resonating speeds, that is 139 and 210 kilometer per hour, which are already calculated. So first of all, we have to know the mid span node, that uh, at which node we want to see the results. So for that, what you have to do is you have to just go to the model. Either you know how you have done the meshing, where the mid span node is there, or what you can do is you just go to this query command, this query nodes, and you can check the distance between two nodes, that which node is coming at exact at the mid span. So like that, what you have to do is the distance is 15.25. So in the similar way, you can check at which node it is the mid span is there. So I have already checked that, and the graphs are already defined here. We just go to the results, time history graph. It will take some time. So then I'll just show how to define this. So in this the mid-span node is node number 21, and this result I'm checking for acceleration at node number 21 for 160 kilometer per hour speed. So you have to just enter the name here. You can enter any name which is convenient to you. Here you have to enter the right node number at which you want to see the results. Then which quantity you want to see. Either you want to see the displacement, velocity, or acceleration, that you have to enter. So we want to see the acceleration, then which direction we want, either in x direction, y, or z. So we want in the z direction for the load case 160. So that is selected here. So that is already selected here. Or you can see the variation of any of the forces with respect to time. So in the time history analysis, you can see the variation of beam forces with the time. From this tab, you have to just add function the similar way, at which node you want to see and for which load case the results you want to see, and just add the function and go to back. It will take some time. So, and then for the selected load case, you just check here and add this from the list. So this result I am showing for mid acceleration for 139 kilometer per hour speed. That is the third harmonic of resonating speed, and just press on this graph. So it will prepare a graph for you, the variation of the acceleration with the time. So it will take some time to respond. So this is the variation of the acceleration at the mid span for 139 kilometer per hour speed. So in the similar way, you can check the variation for any speed or any load case, and at any node you can check. Why we are checking at the center? Because we think rather it is from the mode shape that the maximum response is expected at the center of the span. From here you can also convert this result into Fourier spectrum. What you have to do is you have to just right click here, then convert this time axis to frequency axis. Then it will show you how the results are varying with frequency. So you can just zoom in here for seeing the results. You have to just, you can see, or what I can do the results for you, the presentation. So this is the result for 139 kilometer per hour. So as it is the resonating speeds, you can see the response is continuously building up as the train is as the number of axles are passing the train. In the similar line, the results for 209 kilometer per hour, that is the second harmonic of the resonating speed, are shown here. You can see the clear build up of the response with time, that is with the passage of the train. But this is the results shown at any intermediate speed, that is 160 kilometer per hour. So you can see here first one axle is come, then another is come, another is come. The response is like that. There is no built up of the response because the frequency of the loading and the vibrating frequency of the bridge are much differ from each other. So these conditions we have to avoid while running the trains over the bridges, or you have to just take some measures to change the frequency of bridge, or to uh, cater these excessive vibrations at these speeds. So the next, the Fourier spectra of these results are shown. So this is the Fourier spectra at second harmonic. So you are clearly seen a peak at 4.85 hertz, which is the frequency of our first mode. So it is resonating with the first mode. Then similarly 139 kilometer per hour. So you see a peak at around 4.85 and another peak at around 30.43 hertz, which is at the third mode. So in the speed of 139 km/h, there is third harmonic of the speed corresponding to first mode, but there is also some harmonic of speed corresponding to the third mode also, because the response of the third mode is like that, it is also maximum at the center. Then this is for 160, so you can say it is vibrating with different frequencies, and you can also see that the value that the scale value is very less for this, whether it go up to 6, it is going up only up to 1 or 1.2. So that is why the built up of response is not there for 160 km/h, but built up is there for 139 and 209 km/h. Then now how to see the results at different speeds for displacement or acceleration. For that, what you have to do is to just go to the result tab, and this time history results. If you press this, a new window pop up, so it will take some time to respond. From here you can just click on this button. So a new window pop up which asks at which node you want to see the response and for which load case you want to see. If you select this and just press OK, then a chart it will display, which you can just, so this I have already done because it takes some time. So you have to just go to this and here just enter the node number and select the load cases for which you want to see the result. I have selected all the load cases. Just press OK. So it will showing displacement, velocity and acceleration for different load cases at our selected node. So you can just simply copy this to Excel, or you can copy the results which you want to see. Just select and copy and paste in Excel and further process them. So in this way you can see the results for displacement, acceleration and velocity. And then I'm just showing the final results. So how the results are varying. So this is the mid-span displacement for Vande Bharat train loading. So the orange line is for mode 1 and the blue line, which is the both are just overlapping each other. So these are the results for two, considering only single mode and considering three number of modes. So from here we can see for the displacement we can consider only single mode and the limit is 21.7. So it is well below the limit, but a clear peaks can be seen at around the resonating speeds. But if we see the acceleration response, so we can see that the clear build up in the response is seen with the modes. So that is why it is advisable at least to consider three modes, and a clear peak is seen around the resonating speed, and at this speed it is overshooting the limit provided by the UIC. So in the similar fashion you can do it for any loading and any speed that of interest. So here now this CDA from the bridge rules, that is this formula is given in the bridge rules, and then CDA from dynamic analysis, which is y dynamic upon y static minus 1. This y is the displacement. So this is the UIC formula. So if we calculate the CDA from this analysis, so we can see here that CDA for the bridge rules is a constant line, but from dynamic analysis it seems overshooting at the two resonating speeds. So from here we can interpret that at the speeds other than the resonating speeds, it is a conservative to use CDA for the design, but at the resonating speeds it is underestimating the response. So it is advisable, at least for the if we are allowing the resonating speed over the bridge, so we have to perform the dynamic moving node analysis before designing and multiply to the design forces, the CD obtained from here, or directly we can calculate the forces from here also. So in the similar way, the analysis are performed for the second train. So here the car length is also 24 meters. So the same resonating speeds are expected here also. So in the similar way, analysis are performed. So this is the result shown for the 209 kilometer per hour speed. That is the second harmonic of the resonating speed. So we can see the clear build up in the response when the train is over the bridge, and then it damped out as then it vibrate freely, and the response is going to damp with time. So this is the response for the displacement for the second train. Similar peaks are observed here. Similarly, acceleration, in the acceleration response we also see the peaks at resonating speeds, and this is the CD for the second train. So it also overshoots the limits at resonating speeds. So here it is concluded that for every train, because in this for this train at this speed it is quite close, but here it is overshooting. But for the previous one, it is overshooting at both the locations. So here we have to decide every time that for which train how it behaves. So that is all from my side. Thank you.
Thank you, Mohit. Uh,
Thank you, sir.
So is there any question regarding that? So we can take up the questions first if those are there. Otherwise, we are just approaching 7. So,
right, sir. We
so is
have
there
a
any
few
question?
questions. Yes, sir. Just give me a minute. Sir, Vidhan is asking for amplitude matching. How can we get the scale factor to modify the time speed data? The scale factor you showed for amplitude matching is for frequency domain response factor. Is the same is applicable for time domain also?
I couldn't understand. So amplitude scaling.
Right. Means the amplitude scaling we do in PNNGA website.
Uh-huh.
Is that applicable for time domain also?
I think that is for time domain only. Or as far as I understand, the time domain scaling is done by increasing the amplitude or the scaling the ground motion by a constant factor. So that is called time domain scaling, and we can increase or decrease the response spectrum by the same factor as we are using in the multiplication. So all frequencies get amplified by the same factor, and hence the response spectrum also get scaled by the same factor.
Okay, sir. And Sugandha is asking, while amplitude scaling to the code spectrum, shouldn't we also check the rotated ground motions to match the spectrum, as it is not necessary that the maximum PGA during an earthquake event occurs in the orthogonal direction in which the ground motion is recorded?
Again, the question is not very clear, but what I
Sir,
understand is,
yeah, I think so. It is regarding ROD D100 and ROD D50. Means the recording of the ground
yeah,
motion is in
hmm,
two orthogonal directions, but
hmm.
the maximum or the original ground motion will not be in that direction.
Yeah, but if we record any two components of a ground motion, that describes all the components. So any two component, any two orthogonal components we are recording, those orthogonal components will remain same, and we can uh, decompose those, we can resolve those components in any other direction. So we require only two component, two horizontal components, and of course one vertical component. So we require only two horizontal components to describe any motion, any ground motion. So those two components are enough, and maximum direction will also be obtained from those two components only. That in which direction the maximum ordinate will occur. So if we are taking two components of the ground motion and scaling them, but while scaling, we have to be clear that which is your how your target response spectrum has been obtained, whether it is obtained SRSS or it is the maximum component response spectrum, or it is dot 100 or dot R dot 100 or R dot 50. So sorry, dot D dot 100 and D dot 50. So using that, so same processing you should do on your recorded ground motion as you are having in your target response spectrum. So if somebody is using response spectrum of American code for an American site, then the process will be different. If we are using Indian code, so in Indian code it is just the maximum ordinate out of the two. So whichever is the maximum component, recorded component, that has been considered.
Sir, now, Mr. Deol is asking, what are the names of the checks for bridge design after analysis of a bridge in MIDAS software with the ASTRO code limit, like as lateral and vertical deflection, torsional irregularity, etc.
What is the need for?
What are the names of the checks for bridge design?
Names of
The checks for
check.
bridge design, right?
So which checks are required?
Right. Right.
So which checks are required after all these checks have been done? That's the question.
After analysis of a bridge in MIDAS software with ASTRO code
I
limit.
mean, software can be any, software is not important. So what checks are required after performing what?
After analysis of a bridge in MIDAS software with the ASTRO code limit.
I mean, I'm not sure when you are selecting the command of ASTO code, what checks it is applying. So if you are designing any bridge for India, you have to follow IRS or IRC code, and whatever checks the ULS and SLS checks, which are specified in the IRC codes, those checks you have to apply. So again, question is not very clear to me. Perhaps there is a command where you can apply ASTO check, ASTO code in MIDAS and use it as a black box and assume that everything has been done okay. That may not be correct. So you have to understand what checks actually it is applying and whether it is taking care of all the code requirements of IRC or IRS or not.
Okay, so, Mr. Sandeep is asking, how can we control the frequency within 30 Hertz in the moving load and dynamic analysis, especially for railway gauges?
How can we control frequency within 30 hertz? We are not controlling frequency within 30 hertz. We are considering the modes up to frequency of 30 hertz because the modes are arranged in terms of in the order of increasing frequency. So we will consider all those modes which are having frequency up to 30 hertz. Those modes which are having frequency more than 30 hertz, those are not expected to contribute much in the moving load analysis. That's why those modes, higher modes which are having frequency larger than 30 hertz, those can be ignored.
Okay, sir. Subhrej Jyoti has a doubt regarding scaling of ground motion. While defining the mean spectra for scaling of a number of ground motions to match the target response spectra, should we use geometric mean or simple mean, or both mean values of the group are accepted?
So nowadays it is neither geometric mean nor arithmetic mean. We are using the concept of rod D50 or rod D100. So we resolve the ground motion at different angles and calculate the response spectrum in different directions. And then we take either the envelope of those or the median of those at different periods. So that is the method which is followed in ASC 7. So our code, it is just being revised. So their new response spectrum is coming based on ESHA, but it is not clear from the draft that which method they have followed. So the method to be followed has to be the same which has been used to obtain the target response spectrum. So for example, if the target response spectrum is obtained from a site-specific hazard study, so in that site-specific hazard study also, which definition of the response spectrum we have used, same definition we should use while scaling the ground motions.
Okay, sir. What are the softwares in which we can do fatigue analysis?
I think that question perhaps Ashwin can answer. I have no idea that which software, but I think you can do. Basically, it needs time history analysis. So time history analysis you can perform in any software. You can perform in SAP, CSI Bridge, or VIDAS. But then you have to do the counting of the cycles, so that for that rain flow or some other method of counting is to be required. For that, I don't think any available software, as far as I understand, is having the procedure, but those procedures are available in MATLAB. So one has to combine MATLAB with those procedures.
Okay, sir. Mr. Bharat is asking, while performing such dynamic analysis, should we apply the dead weight as time-dependent load, or the static weight can be combined with the same?
What dependent load?
Time-dependent load.
That weight is not time dependent load. That weight is a constant. So that is the weight of. Okay, so perhaps his question is that how we are going to assign in the software. Okay, so in linear analysis, if you are performing a linear time history analysis, superposition is valid. So you can perform analysis for that load as a separate static load case, and you can perform the analysis under moving load separately, and you can superimpose the two. So under live load, you can perform a dynamic analysis. Under dead load, you can perform a static analysis. And the results of static and dynamic analysis can be combined for any member or for any node. If we are calculating even the displacement, we can combine those two. Problem will occur in case of nonlinear analysis, because nonlinear analysis depends on the history of application of the load. So there we have to first perform a static analysis under dead load. Then whatever are the results after the dead load analysis, this static analysis for dead load, we will consider as the initial conditions for nonlinear time history analysis. But in this course, we have not talked about nonlinear time history analysis, so I don't think the question is related to that. So in case of linear time history analysis or any method of linear analysis, whether this is mode superposition or otherwise, we can first perform static analysis for dead load, and then we can perform a dynamic analysis for live load, and we can combine the results.
Okay, sir. Maybe we can take last few and get the feedback.
Yeah.
Right.
I think you share that feedback. In the meantime, they can give, the survey can go on in parallel. So please answer to this feedback. Your feedback is very important because it will help us in planning our future courses and whether we should do this type of courses or not. So that is also important. So